Physicists have, for some time, been captivated by dark openings, a peculiarity that has charmed researchers for over a century. These gigantic elements, which oppose how we might interpret gravity, remain to a great extent imperceptible to us. A dark opening with a mass that could be 2 to 4 million times that of the Sun is extraordinarily strong, yet because of the research led over the course of recent decades, we've changed from knowing basically nothing about them to uncovering an ever-increasing number of them, sometimes in astonishing ways. As of late, an advancement has happened. Specialists, including those at the Kaku organization, reported that they've figured out how to look inside a dark opening. This new information has enlightened features of the universe that science might have neglected in the past. We should dive into dark openings and discover what exists in space is huge and inspiring. Yet, prior to diving into what was uncovered in ongoing discoveries, it's pivotal to get a handle on the basics of what dark openings are. Many people are familiar with dark openings, but there are still significant gaps in how we might interpret them. The idea of a dark opening turned out to be hypothetically conceivable in 1916, when Albert Einstein published his general theory of relativity, which predicted the existence of such objects. However, dark openings remained simply speculative until the 1960s, when researchers first noticed indisputable evidence supporting their reality. While studying the binary star system Cygnus X1, cosmologists identified an unusually radiant blue star emitting X-rays. This star was not an ordinary heavenly body. It was orbiting around a mysterious, massive object. After further examination, it was clear that the X-rays were not just floating around in space but were being pulled toward the dark substance, confirming the presence of dark openings. This was a momentous discovery, showing that dark openings were not only hypothetical constructs but real phenomena. The significance of this discovery couldn't be more profound. It meant that a completely new class of objects existed in space, requiring urgent and careful study. Specialists from around the world directed their focus toward dark openings with renewed attention. The first identified dark opening, Cygnus X1, is situated around 6,000 light-years from Earth in the Cygnus constellation. It is typically brighter than our Sun and has a tremendous gravitational pull so strong that not even light can escape from it. For this reason, it's called a dark opening. The concept of a dark opening is both fascinating and terrifying. It refers to a region in space where the gravitational force is so extreme that nothing, not even light, can escape its pull. Anything that gets too close to a dark opening is inevitably drawn in, destined to be lost forever. This peril makes the study of dark openings not only fascinating but also crucial. However, are we in any imminent danger from them? Despite the closest dark opening being around 500 light-years away, this distance still raises questions about potential risks. However, the true extent of dark openings is still emerging. After the discovery of Cygnus X1, astronomers began searching for other dark openings. It is now believed that there might be upwards of 100 million dark openings in our Milky Way galaxy alone, though identifying them remains a significant challenge. Estimates suggest that millions of them exist within our galaxy, highlighting the importance of studying these mysterious objects. The primary concern with dark openings is their immense gravitational pull. This pull is so strong that it drags everything, even light, into itself. The center of the dark opening, known as the singularity, is where all the matter that falls into it is compacted into an incredibly dense point. In simpler terms, dark openings act as cosmic vacuum cleaners, sucking everything in their vicinity. If someone were to fall into a dark opening, they would be gradually stretched and compressed until they were reduced to a singularity. This process is incredibly slow, meaning the person would meet their end long before the final, irreversible stage. Yet, despite the apparent danger, dark openings are so pervasive that they cannot be ignored. Even though the closest one is far away, the sheer number of them within our universe makes them a critical subject of scientific investigation. In 2019, scientists achieved a historic milestone by capturing the very first clear image of a dark opening, the supermassive dark opening at the center of the M87 galaxy. This photo was taken over several nights, and with each exposure, new insights were gathered. The data was then meticulously processed to reveal a clearer image. The most striking revelation was that a dark opening is not a single void in space. It consists of three distinct layers. The first layer is known as the event horizon, which marks the point beyond which nothing can return. Once an object crosses this boundary, it is inevitably drawn into the dark opening. The second layer is known as the photon ring, where light is caught in orbit. Any light that enters this region is trapped in the dark opening's gravitational grip and can't escape. Finally, the third layer is the singularity, where matter is crushed down to a single point. The discovery of these distinct layers has provided astronomers with an unprecedented understanding of dark openings. The event horizon, as the boundary beyond which nothing can escape, remains one of the most studied features of dark openings. It is here that the immense gravitational forces begin to take full effect. Objects that cross this boundary are inexorably pulled toward the singularity at the center, where the laws of physics, as we currently understand them, break down. The photon ring, which marks the second layer, is particularly fascinating because it reveals the way light behaves in the extreme gravitational environment of a dark opening. Light that is caught in the photon ring is effectively trapped in orbit, circulating around the dark opening in a way that is both mesmerizing and mysterious. This phenomenon is not just an optical illusion. It is a result of the immense warping of spacetime caused by the dark opening's gravity. The study of the photon ring has provided scientists with valuable clues about the nature of dark openings and their effects on the surrounding space. At the heart of the dark opening lies the singularity, where matter is crushed to an infinitely small point. Here, the gravitational forces are so strong that they overwhelm all other forces, including the forces that typically govern the behavior of atoms and particles. The singularity represents a region of space where our current understanding of physics cannot explain what occurs. It is a place where the fundamental laws of nature, as we know them, seem to break down. Despite the extreme conditions around dark openings, there is still much to learn. The discovery of these features has opened up new areas of research, and scientists are working hard to unlock the mysteries of these enigmatic objects. They are studying the way dark openings interact with their surroundings, the effects they have on nearby stars and galaxies, and what happens when matter falls into them. While dark openings may seem terrifying, they are also some of the most fascinating objects in the universe. They challenge our understanding of gravity, space-time, and the nature of reality itself. As technology continues to improve and our understanding of dark openings deepens, we may one day unlock even more secrets about these cosmic phenomena. For now, however, they remain a symbol of the vastness and mystery of the universe, offering both awe and wonder to those who study them. Space-time is establishing a climate where the laws of physical science, as we probably are aware them, quit working. This breakdown of the laws of physical science is one of the many reasons concentrating on dark openings is so difficult and entrancing. It's considerably more charming that each dark opening acts diversely. While they will quite often have the same essential design, the manner in which each one works can change. Dissimilar to different articles in the universe that we can concentrate on straightforwardly, dark openings must be inspected by implication. Scientists use observations of the radiation transmitted by dark openings and the gas and residue encompassing them. It's difficult to send a test into a dark opening, since anything that crosses the event horizon is maneuvered into the peculiarity, where it would be squashed to an imperceptibly small point. This presents a huge constraint for researchers. Without the capacity to concentrate on dark openings in the conventional manner, scientists are compelled to work with two-dimensional models to comprehend these three-dimensional objects. Moreover, dark openings come in various shapes and sizes, making it significantly more challenging to concentrate on them. Researchers have fostered several hypotheses to make sense of how they form, with one of the most unmistakable being that dark openings begin from falling stars. When a star runs out of fuel, it can no longer create the energy required to balance the power of gravity, causing it to collapse. If the star is gigantic enough, this breakdown continues until the star turns into a peculiarity. NASA analysts have zeroed in on an especially strong world, M87, where they observed a tremendous whirlpool of hydrogen gas pivoting at a shocking velocity of 1.2 million miles per hour. Regardless of the enormous forces at play, the gas didn't fly apart, leading researchers to presume that there must be a huge object at the center of the galaxy maintaining control. This object turned out to be a dark opening, gauging billions of times the mass of the Sun. In 1963, New Zealand mathematician Roy Kerr utilized Einstein's conditions to provide a model for rotating dark openings. Kerr's hypothesis suggested that, rather than imploding into a specific point, a rotating dark opening could form a ring of fire or a growth circle. This disk would turn so quickly that the outward forces would counterbalance the gravitational collapse. Kerr's work also introduced the concept of the Einstein-Rosen bridge, or wormhole. A wormhole is a theoretical passage that connects two far-off points in spacetime, potentially even linking parallel universes. The concept of wormholes has intrigued researchers for a long time. If dark openings are indeed connected to wormholes, they could offer a shortcut through spacetime, allowing travel between distant regions of the universe or even between different times. However, regardless of whether wormholes exist, it's improbable that we would have the ability to travel through them anytime soon. According to Einstein's theory of special relativity, the speed of light is the ultimate limit for how fast anything can travel, presenting an obstacle for using wormholes for faster-than-light travel. Nevertheless, wormholes remain a captivating topic of theoretical investigation. If they were solved, they could provide a way to traverse vast distances of space or even different times. Some physicists also suggest that wormholes could offer a mechanism for time travel. However, the challenges of crossing a wormhole are immense, as they would likely be unstable and surrounded by extreme radiation and gravitational forces. To truly understand the nature of dark openings, physicists must develop a unified theory that combines both Einstein's theory of general relativity and quantum mechanics. One promising contender for this theory is string theory, which suggests that the fundamental particles of nature are really tiny vibrating strings. These strings could explain many of the puzzling phenomena observed, including the formation of dark openings and wormholes. String theory also proposes that dark openings, wormholes, and other intriguing solutions to Einstein's equations might arise due to the bending of spacetime by these minuscule strings. Despite its contributions, string theory requires the existence of extra dimensions of spacetime that are too small for us to detect. Nevertheless, research into dark openings and their mysteries continues to push the boundaries of our understanding. One of the most historic ideas connected to dark openings is the concept of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This hypothesis suggests that dark openings are not completely dark but emit faint radiation due to quantum effects near their event horizons. This radiation could cause the dark opening to gradually lose mass over time, eventually leading to its vanishing. Hawking radiation is difficult to detect, however, because of its weak nature. Still, this idea offers valuable insight into the behavior of dark openings and their role in the universe. Dark openings also provide a unique laboratory for studying the interaction between gravity and quantum mechanics. The extreme conditions near a dark opening singularity are where both gravitational forces and quantum effects come into play, making them a critical area of research for physicists attempting to develop a theory of quantum gravity. The study of dark openings may also hold clues to understanding the origins of the universe. Some theories suggest that the conditions near a dark opening could offer insights into the birth of spacetime itself. Furthermore, if wormholes do exist, they could provide a means for exploring vast regions of spacetime, offering more possibilities for interstellar travel. Although these ideas are still speculative, they continue to inspire scientists to investigate the deepest questions about the nature of our universe.